This video is about inverse functions. This is AP Precalculus topic 2.8. If you appreciate this content, please give it a like. An inverse relation will undo a given relation. Every inverse relation can be found by switching each x and y value. In some situations, this process is intuitive, but other times this will not be obvious. Let's consider the concept of inverses in three different ways: numerically, graphically, and analytically. When we approach a concept numerically, we are usually looking at tables. Example 1. Find the inverse relation of the given table. We can find inverses by switching the x's and y's. So this table shows the inverse relation. Notice that the original table is a function because each input value corresponds to exactly one output value. On the other hand, the inverse relation is not a function because the input value of 2 corresponds to two different output values, 3 and 6. Now let's approach the concept of inverse relations graphically. Example 2. Sketch the inverse relation of the graph given. First, we make a table of key values. We can turn this into a table of inverse relation values by switching the x's and y's. By plotting and connecting the inverse values, we sketch the inverse relation. Example 2b. Is the original relation a function? It is. Each input value has exactly one output value. We can see this by the way it passes the vertical line test. Any vertical line will hit the original relation at only one point. Is the inverse relation also a function? No, the inverse relation is not a function. It fails the vertical line test. You can see that in some intervals, a vertical line will hit more than one point. This reveals that this input value corresponds to more than one output value. Here's an important graphical property of inverses. Notice that the graphs of inverses are reflections over the line y equals x. Now let's approach the concept of inverses analytically. Example 3. Find the inverse for f of x equals 3x minus 7. First of all, remember that f of x is another name for y. So the first step of finding inverses is to switch the x and y. So this equation will become x equals 3y minus 7. Next we solve for y. Adding 7 to both sides, we get x plus 7 is equal to 3y. Now dividing by 3, we get 1/3 x plus 7 over 3 is equal to y. Here's another way you might see that last step. If we divide both sides by 3, you might see it written as x plus 7 all over 3 is equal to y. So this is the inverse relation. However, if the original notation was denoted by f of x, we need to denote the inverse relation using this notation. F inverse of x is equal to x plus 7 over 3. Again, the inverse function of f of x is written as f inverse, like this. Rational functions look like fractions because they are the ratio of two polynomials. Here are the steps for finding the inverse functions of rational functions. Pause the screen to take notes. Remembering that f of x is another name for y, the first step is to switch x and y. Next, you want to eliminate the fraction by multiplying both sides of the equation by the denominator. On the left side, I am going to distribute the x, so I'm going to get xy plus 3x is equal to. On the right hand side, the y plus 3 cancels out, so I'm left with just y minus 2. Next, we want to get all of the terms that have y in it on the left side of the equation, and all of the terms that do not have a y need to be on the right side of the equation. In other words, I'm going to move this term over here by subtracting y from both sides, and I'm going to move this term over here by subtracting 3x from both sides. So we end up with xy minus y is equal to negative 3x minus 2. Remember that our ultimate goal is to solve for y. So the reason why we got all of the y's on the left is so we can factor the y out as a common factor. Think GCF. So if I factor a y outside of parentheses, that's going to leave x minus 1 on the inside. Remember, when you factor out a common factor, to find out what's left on the inside of the parentheses, you divide by the common factor. xy divided by y leaves x. Bring down the minus. Y divided by y is 1. Now we can get y by itself by dividing both sides of the equation by the x minus 1. This is the inverse relation. Don't forget to write f inverse instead of y. If this were a multiple choice question, you might see the answer written in a slightly different way. When the leading coefficient is negative, they will sometimes factor the negative sign outside of parentheses like this. In fact, they often put the negative sign way out in the front like this. I encourage you to pause the screen and try part B by yourself. The first step is to switch x and y. So we have this. Next, we want to eliminate the fraction by multiplying both sides of the equation by y minus 3. On the left side, I will distribute this x. So I'm going to get xy minus 3x is equal to, on the right side, the y minus 3 cancels out. So I'm left with 2y plus 1. I need to get both of the terms that have a y in it on the left-hand side, and this term that does not have a y needs to be on the right-hand side. So I'm going to move this over by subtracting 2y from both sides. And I'm going to move this over by adding 3x to both sides. So I end up with this. The point of getting both of the y terms on the same side is so I can factor that y out and sort of collect it into a single factor. I can figure out what goes on the inside of the parentheses by dividing each of these terms by y. xy divided by y is x. Bring down that minus. These y's cancel out and leave a 2. So I have y times x minus 2 is equal to 3x plus 1. I can get the y completely by itself by dividing both sides by x minus 2. So on the right side of the equation, I'm going to have 3x plus 1 over x minus 2. Since this is the final answer, instead of writing y, I'm going to write g inverse, because that's the proper notation. So that's how you find the inverse of a rational function. Let's say a bit more on graphing inverses. We know that to find an inverse, we simply switch the x and y values. We know that graphically this means that a function and its inverse will be reflections over the line y equals x. We can use this fact to help us graph an inverse when the original function is not simply line segments. Here are the steps to sketch an inverse graph with non-linear pieces. Step 1 is to sketch the line y equals x on the graph. Step 2 is to mark any points on the original graph that are already on the line. These points will stay the same. Step 3 is to select a few additional points on the original graph and find their inverse points. You can find the inverse points by switching the x and y values, or graphically reflecting each point over the line y equals x by drawing a perpendicular from the point to the line y equals x and extending it an equal distance on the other side of the line. Step 4 is to sketch the inverse graph by connecting the new points in a similar pattern to the original function. Example 5. Sketch the inverse of the functions below. Here's the line y equals x, which you should draw as a dotted line. Notice that this point and this point from the original graph are on the line y equals x. These points will not move, so these are 2 points on the inverse graph already. In addition, the point 0, 4 will become the point 4, 0 on the inverse graph. So that's right here. Also, the point 2, 0 will become the point 0, 2. And that's right here. When we connect the points in a similar way as the original, we get the inverse graph. Part B. Here's the line y equals x. These points from the original graph are on the line y equals x, and therefore they will also be on the inverse graph. This key point from the original graph is about negative 1.2, 2.2. The corresponding point on the inverse graph will be 2.2, negative 1.2, which is about right here. Another key point from the original graph is about 0.5, negative 0.5. So the corresponding point on the inverse graph is negative 0.5, 0.5, which is about right here. I begin to draw the mirror image using the key points. So this first part of the graph that goes up to this key point right here, the mirror image goes to this key point right here. From there it falls into the origin, so I do the same. Finally, it takes this little loop through key points, so I mirror that through these key points. And that's it. When you step back and look at the combined image of the original function and its inverse, the line y equals x should split the double image right down the middle symmetrically. So what do inverse functions do anyway? If you plug a number into a function, it generally will output a new different number. For example, if we plug in x equals 2 into the function f of x equals 3x minus 1, we get 5 for the output value. Now if we plug that answer into the inverse function, the answer should be 2. This is because an inverse function essentially will undo a function. So if we plug x into a function, and then plug the output into the inverse function, we should end up with x again. In other words, two functions f and g are inverses if and only if f of g of x is equal to x and g of f of x is also equal to x. So, to show that two functions are inverses, we must show that the composites f of g of x and g of f of x both equal x. Example 6. Let f of x and g of x be the functions below. Determine if f of x and g of x are inverses. The first step is to find f of g of x and see if we get x. So f is the outer function, which is 2x minus 3. So we need to write this with parentheses instead. So 2x minus 3 becomes 2 parentheses minus 3. And we plug in g of x. But then we know that g of x is this expression. So let's make that substitution. So we get 2 times 1/2 x plus 3 over 2, and then minus 3. But now we can do the distributive property. So that's going to give us x plus 3, and then we still have the minus 3. Plus 3 and minus 3 cancel each other out, and we end up with x. So far, so good. Before we go on to step 2, let me emphasize a common mistake that I want you to avoid. Do not try to cancel everything out in one step. The order matters. So don't try to do this. Well, these 2's will cancel out, and these 2's will cancel out, and then the 3's will cancel out, just leaving x. If you go from this step straight to x, you will not get credit. The order of operations really matters here, so you have to show that you distributed first, thus getting the x plus 3, and then, and only then, you canceled out these 3's, giving the x. Step 2 is to find g of f of x, and see if we get x again. Now g is the outer function, so I'm going to rewrite this with parentheses instead of an x. So we will have 1/2 parentheses plus 3 over 2. Inside, of course, we put the f of x. But now we realize that f of x is 2x minus 3, so we make that substitution, and we get 1/2 times 2x minus 3 plus 3 over 2. Now we know not to try to cancel everything out in one step. We must distribute first. So multiplying everything by 1/2 gives us x minus 3 over 2. And then we still have the plus 3 over 2 on the end. Now the minus 3 over 2 and the plus 3 over 2 cancel each other out, and we do get x. We conclude f of x and g of x are inverses because f of g of x equals g of f of x, which equals x. Note that sometimes we must use a restricted domain to ensure that two functions are inverses. For example 7, we need to show that h of x and k of x below are inverses, where x is greater than or equal to 10. This is the restricted domain. Why do you think we had to do that? Well, when you take the square root, the radicand needs to be 0 or greater. So by making x greater than or equal to 10, we make sure that the thing under the radical is 0 or greater. First, we must show that h of k of x is equal to x. H is the outer function here, so let's rewrite h using parentheses instead of x. X squared plus 10 becomes parentheses squared plus 10. And inside goes k of x. But k of x is this radical expression. So we rewrite the square root of x minus 10 squared plus 10. On the next step, the radical and the exponent will cancel each other out, and then we can cancel out the tens. But one more time, let me emphasize that you cannot do this all in one step. Do not go, oh look, these will cancel, and then the tens will cancel, so you just get x. You have to show each step separately to show the order. So yes, squaring the radical makes the radical go away, and we end up with the x minus 10. Then we still have the plus 10 on the end. Now these cancel out, and we do get x. Next, we need to show that k of h of x also ends up giving us x. This time k is the outer function, so I will rewrite k with parentheses instead of an x. So the square root of x minus 10 will become the square root of parentheses minus 10. And inside the parentheses goes h of x. Substituting x squared plus 10 for h of x gives us this. The plus 10 and the minus 10 will now cancel each other out, so we end up with the square root of x squared. Now the radical and the exponent can cancel each other out, and we do get x. Then we write the conclusion. H of x and k of x are inverses because h of k of x equals k of h of x, which equals x. Example 8. Show that n of x and p of x below are inverses, where x does not equal 0 and x does not equal 4. We had to include the restriction x cannot equal 4, because if x equals 4, you get 4 minus 4, which is 0. Now you're dividing by 0, which is not allowed. Of course, x could not be allowed to be 0, because we have 6 divided by x, and 6 divided by 0 is undefined. First, let's show that n of p of x is equal to x. In this case, n is the outer function. So let's rewrite it with parentheses instead of an x. So 6 over x minus 4 becomes 6 over parentheses minus 4. And inside the parentheses goes p of x. However, p of x is this expression. So let's make that substitution. Now we have this. These parentheses are not really doing anything. In fact, I didn't even have to write them. The plus 4 and the minus 4 will cancel each other out. So on the next step, we get 6 over 6 over x. When you divide by a fraction, you multiply by the reciprocal. So this will be 6 times x over 6. Now these 6's cancel each other out, and we do get x. Now let's find p of n of x, and show that we again get x. P is the outer function, so let's rewrite p with parentheses instead of an x. So 6 over x plus 4 becomes 6 over parentheses plus 4, and in the parentheses goes n of x. We don't actually need the parentheses because the fraction bar is its own grouping symbol. N of x is this whole expression. So let's put all of this in the denominator. Now we have this. When you divide by a fraction, you multiply by the reciprocal. So this part of the expression will become 6 times x minus 4 over 6. And then we have the plus 4 on the end. These 6's will cancel each other out. So we are left with the x minus 4 from the numerator, and then the plus 4. Of course, the minus 4 and the plus 4 cancel each other out, and we do get x. Finally, we conclude that n of x and p of x are inverses because n of p of x equals p of n of x, which equals x. Hey guys, don't forget to like and subscribe. But also, if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.